Welcome, everybody, to the last class of the semester. And what I wanted to do at this class is just to give you some summary, some videos to actually summarize some of the things that we've seen and maybe tie a few ends together from some of the stuff that you learned. And I'm going to show you a series of 3 videos. Very short, they're only 3 or 4 minutes each. One of them talks about supernovas, and one is how all the elements in the universe came to be. How did we get hydrogen, helium, iron, oxygen, nitrogen? How did we get those? How did we get some of the heavier elements like lead, gold, platinum? How did we get those? And that's they're formed in supernovas, and that's what this video is going to talk about. The next one is on the size of the universe. How big is the universe? We know, hopefully we know, that the universe is 13.5 billion years old. Okay, so we figure, well, if you look out in one direction, the furthest you'll be able to see is 13.4 billion years. And if you think about it, if you look in a circle, you look 13.4 billion years out one way, and the opposite way, 13.4 billion years. The universe should be double that, 26.8 billion light years in diameter. It's not, though. It's quite a bit bigger. Why is it bigger? That's one of the things we want to understand. And then finally, it sounds like a silly question, but why is the sky dark at night? Okay, and it's not because we go on the opposite side of the earth in the shade and it gets dark. It turns out the night sky is full of stars, and no matter how you go in every direction, there's so many stars in the universe that your line of sight will always fall on a star. So why isn't the sky bright at night from all the stars? That's something called Olber's paradox. And there's a very good explanation for why Olber's paradox. Why don't we see the sky uniformly bright? Because every line of sight should wind up on a star. So these are the 3 topics we're going to talk about today. I want you to see some of these videos. I'll discuss them after you watch them. And then one of these, I'm going to ask you a question on the final. Will come from one of these videos. So I'd like you to watch them all. They're not very long. And we'll talk about them as we go forward. So let's go to the first slide. Let's watching this one.
You can't build a world like ours from simple gases, such as hydrogen and helium. You need all sorts of other elements. You need elements like oxygen and carbon and iron and many more. But we got lucky yet again, because the very same process that causes the stars to shine also just happens to make materials like oxygen and carbon and iron. Stars, simply by accident, are giant factories. To see a star in action, let's imagine I could split one in half. Just as in the soccer ball star, the hydrogen atoms are fusing together, creating helium, which produces the star's energy. But helium is slightly heavier than hydrogen, so it sinks to the center of the star. And now the helium atoms take center stage. As they fuse together, they produce even more energy and form yet another new element, carbon. A vital building block of every living thing. The process repeats itself over and over, and the star becomes layered like an onion. A really big onion. The closer to the center, the heavier the elements, like neon, oxygen, and last of all, iron. Now things change. Iron doesn't produce energy when it fuses, so the fire begins to go out. More and more iron builds up in the star's core until almost all the remaining fuel runs out. Now gravity takes over and squashes the star in on itself. As its core gets more and more compressed, its temperature soars until it's over 100 times hotter than the core of our own sun. Finally, the star collapses and explodes. This is a supernova. The death of a star and the birth of something new. In these brief microseconds, a massive shockwave passes through the star. The blast is so powerful that it forces some of the iron to fuse into even heavier elements. And that's how heavy elements, such as gold or platinum or lead, are made, forged in the heart of an exploding star. So if you have a gold ring, make sure you appreciate it. The metal was made in a blinding flash of light billions of years ago. The finale of the process that produced the elements all around us today. It never ceases to amaze me that our bodies are constructed of the stuff of stars,
and that our hearts beat because of the energy given off as those materials are made. But as magical as a star is, there are even more fascinating and powerful things in our enormous cosmos.
So that was an interesting video. Okay, that was Dr. Stephen Hawking. If those of you who don't know who he is, he has Lou Gehrig's disease, and he's been confined to a wheelchair. He was confined to a wheelchair for many, many years, for about 40 years, and he finally passed away a few years ago. Very famous physicist and astrophysicist. But this video discusses supernovas. And a supernova is an explosion of a very large star, usually about 8 times bigger than our sun. When all the elements get used up inside a large star, there's nothing holding up the star anymore. The energy, there's no more energy coming out from the center to kind of push it out, and gravity is always pulling in, so there's always a balance. A star is in equilibrium, we call it. It's in a balance because the energy going out pushes the star out, and then the energy and the gravitational energy is trying to pull it close together. So it winds up as a balance. So once it runs out of fuel, what happens is there's nothing pushing it out anymore, so it collapses and crushes all the material that's inside of it to a tiny little size, and then it just blows up. It just bounces off of itself and it blows up. That's what's going to happen to stars that are about 8 times bigger than their sun. Our sun will not do that. Okay, our sun is too small to become a supernova or a nova. Nova is just a little smaller than a supernova in mass. Our sun is going to become like a white dwarf. But interesting thing is, we know that the way the sun creates energy is that hydrogen fuses into helium. So you have hydrogen, then you have helium, and then on more massive stars, once all the helium is used up, then it forms the next element, which is carbon. Okay, forms carbon. All these elements are formed inside of stars. So all the elements we have in the universe, most of those are formed inside of stars. But something is special about a supernova. A supernova, though, we know occurs for a massive star. I said at least 8 times bigger than the sun. And what it produces, there's a star stops burning, if you will, stops fusion when it comes up to the element iron. After the element iron, no longer, nothing else fuses after iron. So the highest element it could make, and the highest element, I mean, in the periodic table, if you look, the lowest element is hydrogen, helium. I think iron is like number 26. Okay, there's a lot of elements that are a lot higher number, and those are the heavier ones, like lead, gold, things like that, uranium, those are all heavy. Okay, but those are not produced in stars, okay? What happens is when the supernova explodes, that explosion is so violent that the iron that's built up inside the star, then because that explosion is so violent, they fuse and form heavier elements. So the heavier elements, like gold and platinum, are formed in the supernova explosion. So that's the energy that causes those things. That can't happen. There's not enough energy inside a big star for that to happen. It only occurs in supernovas. And that's how we get all our gold and all the platinum that is in the universe, and uranium and all heavy elements like that, lead, are all formed in the explosions of supernovas. And that's how they came to form. That's how we have those. So that's why he said you should appreciate a gold necklace, because, or anything piece of gold, because you know that that was formed in the supernova explosion. So that was a little digression, if you will, into understanding supernovas and where elements came from. So we know the elements up to iron in the periodic table come from inside the star, and then all the elements after iron are formed in supernova explosions. Okay. I want to show you the next video, and the next video talks about. No, sorry, this is it. What is the size of the universe? And as I told you before, one of the things we know is that the universe is 13.4 or 13.5 billion years old. And as I told you, if you look out in one direction, the furthest you can see is 13.5 billion years. You look in the opposite direction, it's another 13.5 billion light years away. So you'd say, well, 13.5 in one direction, 13.5 in the other direction. The universe should be 27 billion light years old, light years across. It's not. It's quite a bit bigger than that. Why is it bigger than that? And this is the video that's going to address that. So let's just watch this.
Exactly how big is the universe? It turns out that this is not a very easy question to answer, and astronomers have been trying for a very long time to get one. Finally, we have been able to make an estimate, a lower limit to the size of the universe. The cosmos that we can see, the observable universe accessible to us, is at least 78 billion light years in diameter, or 39 billion light years in radius. But how can this be? If nothing can travel faster than light, and the universe has only been around for 13.5 billion years, it seems reasonable to think that the farthest a photon can ever travel is 13.5 billion light years in any one direction. At first glance, this appears to violate Einstein's theory of special relativity. Common sense would seem to say that the observable universe must be bounded by the age of the universe. Using this reasoning, the universe should only be 27.4 billion light years across. The reason this isn't the case is that we must take into account the expansion of space-time. We've recently discovered that new space-time is constantly being created. The universe is getting bigger, and this has been happening at varying rates for over 13 billion years. When light leaves a distant star or galaxy, Its photons race out at a fixed speed, 300,000 meters per second, the speed of light. As it travels through space towards our detectors, the universe through which it travels is not standing still. New space-time is created as it travels, so when the photon actually arrives, the distance it has traversed has increased. To see how this works, imagine you and I are on a road, 100 feet apart, and I am going to walk toward you. By analogy, I am a photon leaving a distant galaxy. Imagine further that as I walk, I am traveling at a fixed speed, but the road beneath my feet actually begins to stretch, increasing the distance between us. I will eventually get to you, but it will take longer, and when I do, and turn around to see how far I've come, I will have walked much farther than 100 feet. If I started 200 feet away, it would take me even longer, and I will have walked further still. Each time I increase my starting distance from you, I will always walk farther than the starting separation distance itself. It's as if you keep backing up, moving away from me. There is even a point that if I start far enough away, depending on the rate of stretching of the road, I won't reach you at all. The creation rate of new spacetime is not constrained by the special theory of relativity like a photon is. There is no speed limit for the expansion of the universe. These are galaxies within the Hubble Ultra Deep Field. The galaxies in this image are the farthest we've ever seen. The universe was only 600 million years old when this light was emitted, and much smaller. If a photon leaving this galaxy, after making its long, arduous 13 billion year journey to our detectors, could turn around and see how far it had come, it would learn that while it was traveling, its home galaxy had moved 39 billion light years away. No laws are being violated, no speed limits broken, and no paradoxes created. This photon was bound by Einstein, but expanding spacetime is not. It can stretch faster unhindered by relativity, and driven by forces and energy we are only beginning to understand.
So interesting. Okay, if you paid attention there, we say, why is the universe bigger than just the age of the universe? You know, the age, as I said, roughly 13.5 billion years in one direction, light years in one direction, it's other 13.5 billion in another direction, so it should be roughly 13.5 times 2, look, 27 billion light years across. It's not, it's bigger. And as this video explained, the reason it's bigger is because the universe is expanding. Okay, the universe expands, it's always getting bigger, and they use the analogy of two people on a road, and you can imagine a photon or a light wave leaving a distant galaxy coming towards us. What's happening is the road between us is stretching, so it takes longer and longer for that photon or that light wave to reach us. So the universe is getting bigger due to the expansion, to its expansion rate. So instead of the universe being 13.5 billion light years in one direction, it's now, because of the stretching since the beginning of time, it's 39 billion light years in one direction, 39 billion in the other direction. Therefore, we say the universe is around 78 billion light years across. That's why it's bigger. So it's important to understand what the difference is, why the universe is not bound by its age. And it's not bound by its age because of the expansion rate. And that's one of the things I wanted you to understand. Hopefully you can get that. Let's take a look at the last and final video. And that final video discusses why is the sky dark at night. So let's take a look at that video and then we'll talk about it afterwards.
There is enough luminous matter in the universe to completely light up the night sky, brighter than the surface of the sun. If you add up all the photons spewing out of all of the stars and galaxies and the space in between, there is enough to light up the universe. Yet when we look up at the sky, this is clearly not the case. So, why is the sky dark at night? Many have been thinking about this for a long time. It can be traced as far back as Thomas Digges in the mid-1500s, Johannes Kepler in 1610, and even later by Edmund Halley in the 18th century. And curiously, even Edgar Allan Poe anticipated possible explanations as to why the night sky is dark. But it was not popularized as a paradox until German amateur astronomer Heinrich Wilhelm Olbers began to think about it in the 19th century. It became known, not surprisingly, as Olbers' paradox. Simply stated, Olbers' paradox says that if the universe is infinite and static, then at any given angle from the Earth the line of sight will end at the surface of a star. An infinitely old universe means that there's been plenty of time for the light from every star that has ever shined to reach our eyes. When we look up, there should be a star everywhere, in every piece of sky. And because of this, the sky at night should be just as bright as when the sun is up. The explanation for why the sky is dark instead of a brilliant curtain of light comes from more recent observations and discoveries about our universe made since Olbers' time. In the 19th century, the nature of space-time and the large-scale structure of the universe was not yet understood. Indeed, astronomers didn't even know there were other galaxies besides ours, much less that they were all racing away from each other. From what was known up to about the 19th century, it seemed very reasonable that the universe was infinitely old and unchanging. And in such a universe, Olbers' paradox is a real problem. We now know, however, that the universe is not infinitely old and static. The universe had a beginning, given birth by the Big Bang. This has important implications for Olbers' paradox. Because the universe has a finite age, one reason our night sky is dark is that many photons have not had time to reach us. Those that have lie within our observable universe. This would not be so if the heavens had been around forever. The darkness of the night sky is a characteristic that argues against infinity. But the Big Bang presents us with another paradox. It states that the early universe was awash in photons. Everywhere, hot photons permeated space-time. At this time in our history, the cosmos was truly bright. Given these hot, bright early conditions, shouldn't wherever we look in the sky reveal the remnant of the Big Bang? Shouldn't there be a luminous curtain of light behind every star and galaxy we see? The fact is, this curtain of light is there, but our eyes cannot see it. Due to the expansion of the universe, the wavelengths of these hot, early photons have been stretched over 1,100 times longer than their original wavelengths. The high-energy, luminous backdrop of the early universe is today filled with relatively cool microwave photons, invisible to the human eye after being stretched by the expanding fabric of our universe for over 13 billion years. This curtain is currently being imaged by special detectors, some aboard the Planck Space Telescope, the most powerful microwave telescope ever built. It is giving us detailed views of what was once the brightest ball of energy ever known, the Big Bang. In the end, Olbers was correct. as was Digges, Kepler, Halley, and Poe. They troubled over the notion that the night sky should be as bright as the noonday sun, and in fact it is. What they didn't realize was that the night sky is only dark to us. If they had had eyes sensitive to microwaves, then there would never have been a paradox.
So that was the last video. Another interesting one is, why is the sky dark at night? And it's kind of related again, as we said, to the expansion of the universe. All right. Olbera said that if the universe was infinite and static, infinite means it's been around forever, and static means it's not changing. He said then there have been plenty of time for light from every star in the universe to reach the Earth. So in every direction we look, we should see a star, and the sky should be bright at night. Why isn't it? And then later on we found that, well, the assumption that Olbera's made, that the universe was static and infinite, is not true. The universe is finite. It occurred, the Big Bang occurred 13.5 billion years ago. So it didn't exist for all time. So perhaps there's some photons that have not reached us yet. That's one explanation. And secondly, is we learn that the universe is expanding. And as the universe expands, as something is receding or moving away from us, what happens to the wavelengths of light? Well, they're shifted towards the red end of the spectrum. That's what we call redshift. And because the universe is expanding at such a high rate, those wavelengths are getting stretched so much that no longer will those wavelengths be in the visible part of the spectrum, but they move to below the visible part, into the infrared or microwave region of the spectrum. And our eyes are not sensitive to microwaves. We can't see them. So what happens is the light from the early universe, from the from the time of the Big Bang when everything was formed, that light has been moved into the microwave where our eyes are not sensitive to, and that's why the sky is not bright at night, because of the shifting due to the expansion of the universe, the redshift. And as you saw those pictures towards the end of the video, one of them showed one of the satellites is actually mapping the universe in every direction, and sees that it's bright in microwaves everywhere we look. So if we had eyes that were sensitive to microwaves, the universe would be bright at night. The sky would be bright. But because our eyes are not sensitive to microwaves, and the expansion of the universe has shifted the light way out of the visible region of the spectrum, that's why the sky is dark at night. So interesting things. You had to learn about what redshift was and about what waves were in order to be able to understand this. Okay, so from these three videos we saw, the one on supernovas and the formation of the heavy elements and the light elements within stars, heavy elements and supernovas, about the size of the universe, okay, why is the universe bigger than its age? And the third is, why is the sky dark at night? Between those three, I'm going to try to ask you one question on the final to try to get you to explain to me, to make sure that you understand some of these points. So I'll conclude this now, and I hope you learned something this semester. Okay, it was a pleasure to have all of you in class. As you know, I'm sorry it ended up the way it did with this isolation and quarantine, but let's hope that we get better in the future.